Hello, let us get on with the next lecture. Welcome to this lecture. Just to recap what we have been doing so far, we are looking at the statistical way of looking at classifiers, and we spent almost 2 lectures discussing base classifier and risk minimization. As we will see through the course, risk minimization is the one generic technique that is used again and again in for pattern classification and regression or function learning. So, base classifier, as you have seen, is optimal for minimizing risk. Okay. So, and risk minimization is a good objective. We have seen how we can get base classifier for various special cases. So, given all the class conditional densities, we can derive the base classifier for any given loss function. We have derived it for different class conditional densities, and also last class we saw a special example where the loss function is special in the sense the actions of the classifier are not just class labels, but classifier is also allowed to reject a class pattern, that the classifier has k plus 1 options where there are only k classes. That example should convince you that given any loss function, one can find a minimum risk classifier using the base classifier technique. Okay. As I have also said in the last class, risk minimization is only one of the many possible objectives. There are ways other than a loss function risk minimization to think of classifiers. Essentially, one way of looking at loss functions is that it assigns different amounts of loss to different kinds of errors a classifier can make. So, when you take the risk, which is some expectation of loss, so that is a kind of weighted loss, the final risk through the loss function values tells you how to trade one kind of error versus another. So, given a loss function which defines our acceptable trade offs, risk minimization is one objective. But there are ways other than through a loss function to trade off different kinds of errors, and one such example we considered last class is the Neyman-Pearson classifier, where instead of saying this error is so many times more costlier than that error and hence minimize the total weighted error rate, we are saying that one kind of error should have probability below some alpha and then minimize the other kind of error. So, there are different ways in which I may want to trade one kind of error with another, and Neyman-Pearson classifier is one good example of this trade off. Another thing that we briefly considered last class is the so called receiver operating characteristic curve, which is another way of explicitly affecting such a trade off. Okay. So, since we went through ROC very fast, let us go over that again. A receiver operating characteristic curve is, as I said, another way to visualize trade offs. So, as an example, let us say we have one dimensional feature space, a 2 class problem, with the classifier being h x is class 0 if x less than tau. Okay. So, there is a single threshold, and if x is less than tau the threshold, then I put in class 0, otherwise I put in class 1. We will consider equal priors and Gaussian class conditional density is equal variance. So, we know tau is midway between the two means, and since h x is equal to 0 when x less than tau, we are assuming that the mu 0 mean for class 0 is less than mu 1 the mean for class 1. Now, given the single threshold classifier, we can easily write the expression for probability of error, which we have done in the general case a couple of classes ago. So, what is the probability of error? Priors are equal, so both prior probability is 0.5. So, what are the two kinds of error? If a pattern of class 1 will come whose density is f1 comes below tau, I would have said it is class 0. So, this is one kind of error. So, this is the probability that a feature vector of class 1 will have value less than tau, that is why minus infinity to tau f1 x dx, and similarly a feature vector of class 0 comes with a value more than tau. So, that is why tau to infinity f0 x. Since both f1 and f0 are Gaussian, f1 with mean mu 1 and f0 with mean mu 0 and both variance being sigma, this integral is nothing but phi of tau minus mu 1 by sigma, this integral nothing but 1 minus phi of tau minus mu 0 by sigma, where phi is the standard cumulative the distribution function of standard Gaussian. Okay. When f1 and f0 are Gaussian, is easier to represent this integral in terms of standard Gaussian distribution function. So, what we can see from this expression is as I vary tau, probability of one kind of error may increase and probability of other kind of error will decrease. So, essentially varying tau allows us to trade one kind of error with another. The base classifier, because there is one loss associated with one kind of error, another loss associated with another kind of error, fixes tau based on this weighted sum of losses. So, base classifier is one way in which I can fix the tau, and as we said, tau allows you to trade one kind of error with another. In that sense, we can say the loss function defines the exchange rate between the two kinds of errors. Okay. That is one way of trading off. We can actually look at it in more general terms as follows. The so called receiver operating characteristic, I will shortly come to you as to where this name comes from, is another way to conveniently visualize this trade off. When we have two class classifier, there are 4 possible outcomes of classification decision. I can call either 0 or 1 and the true class can be either 0 or 1. So, there are 4 possibilities, 2 of them are correct decisions and 2 of them are wrong decisions. Let us say E subscript I denotes the probability of wrongly assigning class I. What does that mean? E 0 is that I actually call 0 class 0, but the feature vector actually belongs to class 1. So, E 0 is the probability of wrongly assigning class 0 and similarly E 1. Now, we can write E 0, that is I say class 0, but is actually class 1. What is the probability of that? Is probability x less than tau, that is when I will say class 0, given that x belongs to C 1. Similarly, E 1, when will I say 1? If x is greater than tau. So, is probability x greater than tau given x belongs to C 0. 1 minus C 0 and 1 minus C 1 can be written as complements of these probabilities. The entire terminology comes from, as I mentioned earlier, much of this Bayesian decision theory was developed during Second World War to make right decisions based on radar signals. The idea is looking at the radar signal, I have to call out whether there is an enemy aircraft or not. So, calling 0, let us say, is that there is no threat, calling 1 means there is an enemy aircraft and there is a threat. So, if I call 0, that is I put in class 0, whereas it actually comes from class 1, is called a miss, it is a misdetection. Similarly, if actually there is no enemy aircraft, but I call out a threat, then there is a false alarm. When there is an enemy aircraft and actually call an enemy aircraft, there is a correct detection. If there is no enemy aircraft and I say there is no enemy aircraft, there is a correct detection. So, those are the 4 names, and the receiver operating characteristic name also comes because all this decision theory is embedded into the radar receiver, right, and choosing tau is like choosing an operating point for the receiver. That is why this is called receiver operating characteristics. Okay, coming back, given these numbers E 0, E 1, 1 minus E 0, 1 minus E 1, if I for any fixed class conditional densities, as we vary tau, these numbers keep changing. So, if I choose the point E 1 comma 1 minus E 0 for different taus, I have different values of E 1 and E 0 and hence different values of E 1 and 1 minus E 0. So, if I look at E 1 1 minus E 0 space, which is R 2, and for each tau I note down which is the point, then for fixed class conditional densities, as we vary tau, the point E 1 1 minus E 0 moves along a smooth curve in R 2. See, E 1 is a false alarm rate, 1 minus E 0 is correct detection. So, essentially plotting the false alarm rate on the x axis, correct detection rate on the y axis, and for different taus you will have different points. Okay. So, the curve will look something like this. So, on the x axis you have E 1, on the y axis you have 1 minus E 0, this is the false alarm rate, this is the correct detection rate. For different taus you get different values and it actually moves along a smooth curve. Of course, the curve does not always have to be like this, the curve can have many other characteristics. Such curves are called receiver operating characteristic curves. Okay. Now, the choice of coordinates is arbitrary, but this curve when you for various tau you put the point E 1 1 minus E 0 is called a receiver operating characteristic curve. Okay. For any fixed tau, we can estimate E 0 and E 1 from the training data. I can fix a tau, I can calculate from the training data how many are correctly classified, how many are wrongly classified. I can detect all the two kinds of errors, and hence I can get the fraction of errors, and that is my estimated probabilities. So, I can estimate E 0 and E 1 from the training data, right. Then I can decide as a vary tau, I will get different values of E 0 and E 1, and I can decide which tau is best for me, right. Even if I do not want to, even if I do not know the class conditional densities, as long as the classifier is a threshold based classifier, simply by estimating E 0 and E 1 and plotting them for various values of the threshold, I can get the whole curve and then decide on which point on the curve I want to be. Okay. So, this can be done for any threshold based classifier irrespective of the class conditional densities. When the class conditional densities happen to be Gaussian with equal variance, this procedure is particularly helpful as follows. From our earlier error integrals, we know phi of tau minus mu 0 by sigma is 1 minus E 1, similarly phi of tau minus mu 1 by sigma is E 0. So, I can write tau minus mu 0 by sigma is phi inverse 1 minus E 1 and the other one phi inverse 1 minus E 0. Now, if I know the numbers E 1 and 1 minus E 0 which are the coordinates of the ROC, then I can calculate phi inverse of 1 minus E 1 and phi inverse of 1 minus E 0. Let us say those numbers are A and B. Now, the interesting thing is no matter what tau I have used, if I can correctly estimate this A and B, then the absolute difference between A minus B is mod of mu 1 minus mu 0 by sigma, which is the discriminability. Right. So, whether or not I know the class conditional densities exactly, whether or not I know mu 1 and mu 0, for a I just take a sum tau, estimate E 0 and E 1, hence calculate these numbers A and B using the standard Gaussian distribution function. Then the difference between A and B is the discriminability mu 1 minus mu 0 by sigma, which gives me a very nice method of tweaking in case of Gaussian class conditional densities. I can start with some tau, I can get my E 1 and E 0. Once I have E 1 and E 0, I have E 1 and 1 minus E 0 and hence I can calculate discriminability D. As we derived last class, D completely specifies the base error. So, I know for this problem what is the optimal base error. Then I can ask if the tau I am currently using achieves this error rate. If it is not, I can keep changing tau till I achieve the base error rate. No matter what tau I chose, to the extent I can estimate A and B correctly, I can estimate discriminability correctly and hence I can estimate base error rate correctly. Once I know base error rate, I can keep tweaking tau till I achieve the base error rate. This is one way I can use ROC in case the class conditional densities are Gaussian. Of course, you can use ROC in many other cases. So, suppose I have a linear discriminant function h x is sine of w transpose x plus w naught. If I have somehow estimated w, so I know the right direction onto which to project x, then I can learn w 0 by using an ROC. Here it does not matter what class condition the w transpose x has, just by plotting the ROC I will be able to fix a threshold w 0. So, this is another way apart from name and Pearson classifier to trade off one kind of error with another. Okay. So, that completes our general discussion of classifiers. Okay. In 2 class clear there are 2 errors, loss function is one standard way to trade these errors and risk minimization hence is a very good objective. There are also methods such as Neyman Pearson classifier using the ROC curve, whereby one kind of error can be traded with another kind of error. Okay. Now, let us move back to asking okay, all this is fine if I know the class conditional densities. So, if I want to actually implement base classifier or implement Neyman Pearson classifier, we need the class conditional densities and prior probability. So, let us stick to base classifier. So, how do we implement base classifier in practice? How do I get class conditional densities and prior probabilities? Okay, that is the next question. Now, prior probabilities may not be so difficult. I may know prior probabilities, I may want to assume prior probabilities of 2 classes to be same, or I can simply estimate prior probabilities as the fraction of examples from each class. I got some n examples. if n1 of them are from class one class and n2 of them are from the other class, then n1 by n and n2 by n are good estimates for prior probabilities. Okay. Then how do I get class conditional densities? Examples are IID and class labels of examples are known. I can take the full example set and then separate them into examples of class 0 and examples of class 1. Let us still stick to 2 classes. Of course, this will also work for many more classes, but so give me an example set, give me training data set where some of the patterns will be class 0, some of the patterns will be class 1. So, I separate them out. So, ultimately what I have is IID samples of class 0, IID samples of class 1. What does that mean? If class 0 has density function f 0, I have some samples which are drawn from a density function f 0 in an independent manner and they are given to me. So, I have x 1, x 2, x n, all of them are drawn from a particular density function. Okay. So, the problem now turns out to be given some x 1, x 2, x n which are drawn in an IID manner according to some distribution, let us say the class conditional density f 0, estimate the density correctly. So, now I do not have to look at the 2 classes together. If I can estimate the class conditional density of one class, I can estimate for the other class. So, my problem simply is given a density function and I know there is a density function and then I have got n samples drawn independently from the density function. How do I estimate the density function? So, there are 2 main approaches for estimating density function from IID samples like this. These are called parametric and non-parametric approaches. What is the parametric approach? I assume that I know the density function except for some parameters. That is, I know that the class conditional density from which I got the samples is normal, but I do not know the mean and variance. Right. I may know that the class conditional density is exponential, but I do not know the lambda parameter and so on. So, in the parametric approach, we assume that the data given to us are IID realizations of a random variable x whose distribution is known except for values of some parameters. Then we need to estimate the parameters from the density of the parameters of the density from the samples available. Okay. This is the parametric method. In the non-parametric method, we do not assume any form for the class conditional density, right. Without any form for class conditional density, we want to estimate the density. Okay. Very often is estimated as some convex combination of densities using the sample data I have. We will look at both approaches, but first we will look at the parametric approach. Okay. In the parametric approach, let us say we are getting data from a density f, we will write that density as f x given theta, where theta is the parameter vector, right. So, given theta does not necessarily mean theta is a random variable at this point, but it is simply that we will write f x given theta to denote that the theta is the unknown parameter vector. Okay. So, for example, my theta could be a vector of 2 parameters theta 1 and theta 2, and the density f x given theta, that is specified in terms of theta, is 1 by I am sorry about the typo, this should be root 2 pi, it is not 2 pi, but it is root 2 pi, 1 by root 2 pi root theta 2 exponential minus x minus theta 1 whole square by 2 theta 2. Here this is the normal density with theta 1 as the mean and theta 2 as the variance. Okay. So, f x given theta is normal with mean and variance constituting the 2 parameters. Okay. So, this is what we mean by specifying the parameter vector, okay. That is, the density is known except for the parameter vector. This means that the density is normal, but I do not know the mean and variance, those are given by the unknown parameters theta 1 and theta 2. Okay. Once again I am sorry, this should be root 2 pi. Now, estimation of density is same as estimation of the parameter vector. Okay. So, let us first get some notation in place to discuss about estimation. Let us say x is some random variable which has density f x given theta, that is, I know the density of x except for some parameters theta. From now on, we will not make any distinction between vector and scalar quantities. So, whether x is one dimensional, x is d dimensional, whether it is a feature vector, whether it is a single feature, we use the same x, we do not use any boldface, things will become clear from context. So, x is a random variable which could be a vector with density f x given theta. Okay. An IID sample of size n consists of n IID realizations of the random variable x. Okay. You get n values, n IID values of the random variable x. So, we denote this as x 1, x 2, x n. Okay. Once again, each of these xi's themselves may be vectors if x is a random vector. The entire set of data x 1 to x n we denote by either a boldface x or a script d. Okay. So, this is the sample or data, this is the data I have from the density. We sometimes denote it by the script d or sometimes denote it by the boldface x. Okay. When we want to think of it as a vector, we always think of it as a column vector of x 1 to x n. Okay. Of course, it will be a vector only if x's are scalars. If x's them, if the random variable x itself is a vector, which is often the case because we have feature vectors, then each of these xi's themselves are vectors. Okay. We can think of the data as one realization of the set of random variables x 1 to x n, where each xi has density f x given theta and xi are IID, right. The sample can also be thought of as a realization of the set of random variables x 1 to x n, where xi are IID and each of them has the same density x given theta. Okay. Now, a statistic given data is any function of data. So, if I am given data samples x 1 to x n, any function of the data samples x 1 to x n is called a statistic. Okay. So, essentially when I want to estimate a parameter, okay, it is a statistic. Given the data, I am giving you what the parameter value is. So, the estimator essentially is a function that maps the samples to parameter values. We generally denote estimation such an estimate by putting a hat on the quantity. So, theta hat is an estimate of theta and theta hat is always a function of data. So, we should write it as theta hat of x 1 comma x n. When the data is cleared from context, we will simply write it as theta hat. This theta hat is obtained from n samples, that is the only thing that is really important to us. So, sometimes we write theta hat n to denote that theta hat is an estimate of theta obtained from a sample of size n. Okay. So, whenever it is important to remember the sample size, we put that as a subscript of the estimate, and once again estimate is a statistic, that is a function that maps data to parameter values. So, here is an example of an estimate. So, an estimate obtained to n samples could be theta hat n, could be defined as 1 by n I is equal to 1 to n x I. This of course, is the well known sample mean, and as all of you know, this is a good estimate for the actual mean of the random variable. Okay. So, all estimates are functions of data like this. Okay. Of course, there can be different estimates that are intuitively reasonable. Right. Here are some examples. Suppose x is a Poisson random variable with parameter lambda. Given the sample mean as well as sample variance seem to be reasonable estimates for lambda, right. Lambda for the actual Poisson random variable, both the mean and variance are lambda. So, if you give me a sample, I can take the sample mean as the estimator for lambda, or I can take the sample variance as the estimator for lambda, right. So, both are equally reasonable. If x is normal, let us say with some mean mu and variance unity, as you know, because the normal density is symmetric, both mean and median of the normal density is mu. So, should I take the data mean or should I take the data median? Both of them seem to be good choices for estimating mu. These are just some examples, there are many such questions one can ask. So, one would like some criteria to choose estimators. What should be a good way to choose estimators? So, let us look for some figures of merit for estimators. Ultimately, we need good estimators, right. What does good mean? Good is based on a criteria. So, to decide what is good, I need some criterion, right, some criterion for goodness, and of course, you know, a criterion for goodness should somehow allow me to obtain such estimates for various kinds of densities, right. otherwise the criterion is useless. So, let us ask for some simple criterion. Okay. But anyway, before we go to criterion, the methods that we use in this course, there are only two methods that we discuss. One is called a maximum likelihood estimators, other is called Bayesian estimators. There are many other methods of obtaining estimators, but they are the only two things that we will consider in this course. So, before we get into our methods, we look at some general issues in estimation. So, we first discuss what kind of properties do we want from our estimators, so that we can decide what are good estimators. Then we will ask what kind of methods will give us good estimators, right. So, to start with, we will just discuss general issues in estimation. An estimator theta hat of a parameter theta is said to be unbiased if expectation of theta hat is equal to theta, right. This seems to be a nice thing to ask for. So, when I am estimating theta hat, right, theta hat from data, I obviously make errors. So, the expectation of theta hat is equal to theta means sometime I make errors on one side, sometime I make errors on the other side, so that all errors will cancel out, right. So, at least in an expected sense, theta hat is same as the actual parameter I want to estimate. Of course, we have to be a little careful in understanding what this expectation means. When we are saying expectation of theta hat, that is because theta hat is random, that is theta hat is a random variable. Why is theta hat a random variable? Because theta hat is the function of data, right, x1 to xn, theta hat is the function of x1 to xn, these are IID random variables. So, theta hat is random because theta hat is the function of x1 to xn, because theta hat is the function of x1 to xn. When we say expectation theta hat, we mean the expectation with respect to the joint density of x1 to xn, right, because the joint density of x1 to xn is nothing but n-fold product of the density of xi, which is f x given theta. We are assuming that the density of each x is f x given theta and x's are independent. So, the joint density is simply product of the marginals. So, this expectation here refers to expectation with respect to the joint density of x1 to xn, which is same as the n-fold product of the density model we are using. But then here is the catch: if xi is distributed as f x given theta, then to do that expectation we need the value of theta, right, because theta hat is a function of x1 to xn. I have to do that expectation with respect to joint density of x1 to xn, but the joint density of x1 to xn involves theta. So, what we mean by expectation of theta hat is equal to theta is the following: if I take any parameter value theta, add the true parameter value and then take expectation of the random variable theta hat, then that expectation should be equal to that particular parameter assumed. So, to denote this, under this expectation we will put a subscript and say E theta. E theta is expectation with respect to joint density of x1 to xn, where we assume the unknown parameter has actually value this theta. So, now this equation makes sense in the following way: for any given parameter value in the parameter space, if I assume that is the right parameter and take expectation, I should get back that parameter value. Okay. So, an unbiased estimator theta hat satisfies expectation of theta hat is equal to theta, where that expectation has the subscript theta, as I explained just now what that subscript means. Because once we understand it, to keep the notation simple, we will remove that subscript, we just talk about expectation theta hat knowing this. So, a theta hat is an unbiased estimator if for every density in the class of densities we are interested in, that is every value of the parameter in the parameter space, the expected value of the estimator is the true parameter value. Okay. Here are some examples. Suppose f x given theta is normal with mean theta, okay. The variance really does not matter, but anyway assume variance is unity, and let us say I define the estimator theta hat n, that is estimator obtained from n samples, as 1 by n summation xi. So, what is expectation theta hat is 1 by n summation xi. So, if I assume that xi has distribution f x given theta with parameter theta, then expectation xi is theta. So, 1 by n summation I expectation xi is equal to theta. So, which means expectation theta hat is equal to theta for every theta and all n, because expected value of xi is equal to theta, right. So, the sample mean estimator, this as you can see, this is the sample mean, this is the mean of the data. So, the sample mean estimator is such that expected value of the estimator is the true value of the parameter. Okay. So, this seems good, but before we can say this seems good, we just now defined this as unbiased, right. If this is satisfied, that is called unbiased estimator. So, I know that the sample mean is unbiased estimator, but this is a property that many other estimators have. Sample mean is nothing special about this, right. See, take the example. Let us say theta hat of x 1 to x n is only x 1 plus x 2 by 2. Even though I have n samples, let us say I throw away all but n minus 2 samples and take my estimate as just the average of the first 2 samples. What is the expected value of theta hat? Is 0.5 into expectation of x 1 plus expectation of x 2, which is also equal to theta, right. So, this is also an unbiased estimator. Suppose I take another estimator theta double prime hat, where I take the estimate to be the first value I get. This is also unbiased, right. It is like saying I want to calculate the probability of heads for a coin, I toss it a few times. I can take the number of heads by the number of tosses for any number of tosses, right. It is always unbiased. So, basically what this means is, if I look at this theta hat and this theta prime hat, this theta double prime hat, all the 3 estimates are unbiased. So, saying an estimate is unbiased is not enough, right. It does not really tell me whether the estimate is good or not. So, we can go to the other extreme and say, so what is that we want to say? Obviously, we will our gut feeling that this is a better estimator than theta prime or theta double prime, but on what basis can I say this estimator 1 by n summation x I is better than this estimator, right. So, one way we can ask now is, we will say that theta hat is better than theta hat prime if the probability that theta hat differs from theta by some quantity, that is minus a less than theta hat minus theta less than b, this probability is greater than or equal to the probability for the same a and b for theta hat prime. What does that mean? Theta prime is closer to theta than theta hat prime. The probability of theta hat being closer to theta is higher than the probability of theta hat prime being closer to theta, because this has to hold good for all a b. I hope all of you notice that I put a subscript theta on p, which means to calculate this probability, what this probability is respect to what? The random variable theta hat's distribution needs the 2 parameter. So, what I am saying is, I for whatever theta I assume in the distribution, that is the theta I am going to put here. This is a very strong requirement. No matter what my sample size is, no matter what is the accuracy level I want, no matter what values to a and b I give, theta hat is always more accurate than theta hat prime. So, if we can get this, this will be very good, and then I can always say theta hat is better than theta hat prime, but it is very difficult for any estimator to establish that level of superiority over any other. This means, for all sample sizes, for all accuracies, one estimator is uniformly better than the other estimator, right. That we may or may not be able to establish. So, instead of asking that the error should be better at all levels of accuracy, we will simply say the expectation of the square of the error, that is, this is the mean square error that theta hat has. Theta hat minus theta is the error, theta hat minus theta whole square is the square of the error. If I take the expectation, it becomes mean square error of theta hat. So, we will say theta hat is better than theta hat prime if the mean square error of theta hat is less than the mean square error of theta hat prime, right. This seems a reasonable thing to do because on the average the error in theta hat is smaller than on the average the error in theta hat prime, and hence I am willing to settle for theta hat rather than theta hat prime. Okay. So, this is defined as the mean square error of estimator. MSE of theta hat is defined as expected value of theta hat minus theta whole square. As you can see, all the expectations have theta as the subscript, to say this theta that I use here is whatever the same theta I assume for taking the expectations. Okay. That is when this is actually the error in theta hat. So, expected value of theta hat minus theta whole square is known as the mean square error of theta hat. Okay. Here is a very interesting result. For any estimator, the mean square error of the estimator is given by sum of 2 quantities, V theta theta hat and V of theta hat and B of theta hat square, where V of theta hat is the variance of theta hat, because theta hat is a random variable. What is its variance? Variance of any random variable is expectation of x minus expectation of x whole square. So, variance of theta hat is expectation of theta hat minus expectation of theta hat whole square. The whole square is inside the expectation. So, this is the variance of theta hat. This is the variance of the random variable theta hat. So, we call it the variance of the estimator theta hat. The bias B theta hat is called the bias of the estimator. Bias of the estimator is simply expect value of theta hat minus theta, right. Earlier we defined theta hat to be unbiased if expectation theta hat is equal to theta, right. So, the difference between expectation theta hat and theta is called the bias of the estimator. So, essentially an estimator is unbiased if its bias is 0, and mean square error of any estimator is variance of the estimator plus square of its bias. This lemma is not very difficult to prove. So, let us prove this. Okay. Before we go there, let us remember that if an estimator is unbiased, so that the bias of the estimator is 0, then the variance of the estimator is equal to its mean square error. So, for unbiased estimators, the mean square error is simply the variance. Okay. How do we prove this? What is the mean square error? Expectation of theta hat minus theta whole square. I have stopped putting theta as subscript. Sometimes I will put, sometimes I will not put, but all of us understand what this expectation means. So, I can rewrite this by adding and subtracting expectation of theta hat. So, I wrote theta hat minus theta whole square as theta hat minus expectation theta hat plus expectation theta as minus theta whole square. So, now I can group the first two terms and second two terms and think of this as a plus b whole square and expand. If I expand it, I get expectation of a square, which is theta hat minus expectation theta hat whole square, then expectation of b square, that is expectation of expectation theta hat minus theta whole square. Now, theta is a constant, expectation of any random variable is a constant. So, expectation theta hat minus theta is a constant. So, expectation of that is also a constant, I do not have to take expectation. So, the second term simply becomes expectation theta hat minus theta whole square. The third term is the 2ab from the square, that is expectation of 2 times expectation of theta hat minus expectation theta hat into expectation theta hat minus theta. Okay. Now, concentrate on this 2ab term. The second factor here, expectation theta hat minus theta is a constant, as we already seen. Expectation theta is a constant, theta is a constant. So, this constant can come out of this expectation. If it comes out of this expectation, what is left is expectation of theta hat minus expectation theta hat. Push this expectation inside, I get expectation theta hat minus expectation theta hat, because expectation of expectation is itself, and expectation theta hat minus expectation theta hat is 0. That gives us MSE is this term, expectation theta hat minus expectation of theta hat minus expectation theta hat whole square, that we already defined as the variance of theta hat. The second term by definition is bias square of theta hat. This is the third term where I pulled out the constant out of the expectation. Now, this is 0, giving us mean square error of theta hat is variance of theta plus bias of theta square. Okay. So, for unbiased estimators, low variance implies low mean square error. So, among all unbiased estimators, I can choose the one which has lower variance. So, if I go back to my earlier estimates, when theta hat is the sample mean estimator, when theta hat is the sample mean, because xi's are independent random variables, variance of a sum of independent random variables is sum of variances. So, this will be inside the summation, this the variance of the sum is sum of variances, that will be n sigma square, because I am multiplying with 1 by n, it becomes 1 by n whole square into n sigma square. So, this becomes sigma square by n, right, whereas this becomes sigma square by 2 and this becomes sigma square, right. So, that is basically what I am getting. So, in my earlier example for the sample mean, the variance is sigma square by n, whereas for my other estimators, when I take this, it is sigma square by 2, right. So, because the variance is smaller here than here, this is a better estimate, because both are unbiased, variance is the mean square error. So, the mean square error of this estimator is smaller than mean square of this estimator. So, I can say that this estimator theta hat n is better than theta hat prime n. So, mean square error is a good way to compare estimators, and for unbiased estimators mean square error is simply the variance. So, unbiased estimators with low mean square error are good estimators. Okay. For a given family of density functions, theta hat, a specific estimator theta hat is said to be uniformly minimum variance unbiased estimator, often written as UMVUE, uniformly minimum variance and unbiased, if firstly theta hat is unbiased and mean square error of theta hat, which is same as variance because unbiased, is less than the mean square error of any other theta hat prime, where theta hat prime is unbiased estimator. So, theta hat is UMVUE, that is uniformly minimum variance unbiased, if variance of theta hat is smaller than variance of any other unbiased estimator theta hat prime. Now, this has to hold for every single n, that is what is meant by uniformly minimum variance. We are not saying that at some n is minimum, for every single n the variance of theta hat n is less than the variance of theta hat prime n. So, for every n for all theta, if the variance of theta hat is less than theta hat prime and theta hat is unbiased, then that theta hat is called the uniformly minimum variance unbiased estimator. So, as a matter of fact, if I can get UMVUE, nothing like that, but in many cases difficult to get UMVUE, and also there may not be many standard procedures for getting UMVUE. Okay. So, let us look at some other figures about it. So, everything that we looked so far, we are saying for every single n something has to hold. Unbiasedness is the expectation of theta hat n is equal to theta for all n. We are talking of UMVUE, once again minimum variance at all fixed sample sizes. Now, if we let go of that and only ask for as the sample size goes to infinity, is the estimator good, right? That is also a good way of looking at it. We can think of asymptotic properties of estimators, right. So, one asymptotic property is to say as the sample size goes to infinity, does the estimator converge to the true value, does theta hat n converge to theta. Since theta hat n is a sequence of random variables, at the very end it becomes a sequence of random variables. So, when I say convergence, how do you say convergence in what sense? Is convergence in distribution, convergence almost surely. So, we will take convergence in probability because that is a convenient mode of convergence for our purposes. So, we will say an estimator theta hat is said to be consistent for theta if theta hat n converges in probability to theta as n tends to infinity. This is an asymptotic property, but essentially what this means is because of the convergence in probability, if n is sufficiently large, the probability that theta hat n and theta differ by say some epsilon can be made less than delta. That is what this convergence in probability means. So, a consistent estimate is good because for large sample size the estimator will be close to the true value of the parameter. So, an estimator theta hat is said to be consistent if theta hat n converges in probability to theta. Okay. We know the sample mean estimator converges to two estimators. Sample mean estimator is 1 by n summation x I. Now, by law of large numbers, sample mean converges to the population mean in probability, weak law of large numbers. So, a sample mean estimator, in addition to being unbiased, in addition to being minimum variance, is also a consistent estimator. Okay. Our interest in consistent estimators comes from the fact, okay, before we go there, a consistent estimator does not have to be unbiased. Consistency is an asymptotic property. So, even if the estimator is biased, it may still be consistent, right. For example, let us instead of taking sample mean, I will take 1 by n plus 1 summation x I instead of 1 by n summation x I, is obviously biased because expected value of theta hat n is not equal to theta, but is n by n plus 1 theta. So, there is bias, but as you can see as n goes to large, then whether you divide by n or n plus 1 may not make much difference, and one would expect that theta hat n will converge to theta, and we can prove that, right. This is not an unbiased estimator, but we can prove the following: expectation of theta hat n minus theta whole square. This will, because it is this gives me the mean square error of the estimator. Okay. So, this is theta hat n is 1 by n plus 1 x I. So, I wrote theta as n by n plus 1 theta. If I push the summation inside, I will get n by n plus 1 theta, and the remaining 1 by n plus 1 theta I wrote separately square. Now, you can square this because x i's are independent, when I square it all the cross terms will cancel when I take the expectation inside. So, that will ultimately give me 1 by n plus 1 whole square into only the squares of x I minus theta whole square will be there. So, there will be n such terms which are sigma square. This will give me 1 by n plus 1 theta square and the 2ab term which is 2 theta by n plus 1 whole square into expectation of x I minus theta, which is 0, because if you put the expectation inside, expectation x I is equal to theta. So, which just gives me 1 by n plus 1 whole square and sigma n by n plus 1 whole square sigma square 1 by n plus 1 whole square theta square. As n tends to infinity, this goes to 0. So, expected value of theta hat n minus theta whole square goes to 0 as n tends to infinity, which means theta hat n converges to theta in quadratic mean, and hence it will also converge in probability. So, this theta hat n, what we saw earlier, even though it is a biased estimator, it is a consistent estimator, right, because it as n tends to infinity converges to 2 value. Okay. So, this goes to 0 as n tends to infinity, hence theta hat is a consistent estimator, though it is biased. Okay. So, consistency is not same as unbiasedness. So, unbiased estimators can also be consistent, as we said sample mean is consistent. A biased estimator can also be consistent, but the good thing about consistency is that we have a general procedure for obtaining consistent estimator. Maximum likelihood estimation is a general procedure for obtaining consistent estimators. It is a parametric method. We estimate parameters of density based on ID samples, and the nice thing is if the density satisfies some simple regularity conditions, then the maximum likelihood estimates can be proved to be consistent. Okay. This is how we do maximum likelihood estimation. Once again x1, x2, xn be the samples. The likelihood function, we define a likelihood function which is a function of x and the parameter vector theta as L x theta is product j is equal to 1 to n f x j given theta. Okay. So, for we have always been talking of f as density, but it really does not matter. If the samples are from a discrete random variable, f is taken to be the mass function. If they are taken from a continuous random variable, f is the density function. In both cases, we define this product as the likelihood. Intuitively, if it is the density function, if it is the mass function, this product gives you the probability of obtaining the sample. If it is density, of course, is not a probability, but even then it is called the likelihood. Of course, the reason for calculating likelihood is not about calculating about xj, because xj is in any when I am estimating I have got specific sample and I am estimating theta. So, we often would like to think of likelihood, or not often, we always think of likelihood as a function of theta with the sample being known. The sample is data. So, to emphasize this, we often write theta as the first variable, or more often we write it as L of theta given x or L of theta given d, because d is the notation for samples. We always write the likelihood function as L of theta given x, L of theta given d, because likelihood function is viewed as a function of theta. Okay. So, the maximum likelihood estimate is the value of theta that globally maximizes the likelihood. I said we look at likelihood function as a function of theta. So, theta star is MLE, that is maximum likelihood estimate for theta if L of theta star given x is greater than or equal to L of theta given x for all theta. So, the value of theta that globally maximizes the function L theta given x is called the maximum likelihood estimator. Okay. So, finding MLE is essentially an optimization problem. If I am given the function L theta given x as a function of theta, I have to find its global maximum. Okay. This is an optimization problem. Very often for convenience in the optimization, we take what is called the log likelihood. We take the log of the likelihood function. The reason is likelihood function, as you have seen, as the product. So, if I take log, it becomes summation. Okay. So, log of L theta given x is summation of log of f x j given theta, and we represent the log likelihood by little l given theta x, likelihood as capital L and log likelihood as small l. Now, the ML estimate would be maximized the log likelihood, because log is a monotone function, whatever maximizes the likelihood will also maximize the log likelihood. So, for many densities we can analytically calculate the maximizer, and if you can't, of course, you can always use a numerical technique if we know the likelihood function to obtain the ML estimate. So, let us consider one example. Let us say one dimensional case, let us say x is normal with mean mu and variance sigma square. So, there are two parameters theta 1 and theta 2, theta 1 is mu and theta 2 is sigma square. Okay. So, we have taken theta to be sigma instead of sigma square, we could have taken the second parameter to be sigma square or sigma, we have taken to be sigma, then the density becomes 1 by theta 2 root 2 pi exponential minus x minus theta 1 whole square by 2 theta 2 square. Okay. So, what is my likelihood? L theta given x is product over j is equal to 1 to n f of x j given theta, f of x j given theta is the same expression where x is now replaced by x j. Okay. Now, what will be the log likelihood? It is log of this. So, log of this will be sum and log of this will be log of the first term plus log of second term, log of exponential will be only what is inside the exponential. So, that becomes the log likelihood, sum j is equal to 1 to n, log of this will be minus log theta 2 minus half log 2 pi and then what is inside. So, minus log theta 2 minus half log 2 pi minus x j minus theta 1 whole square by 2 theta 2 square. So, this is the log likelihood function. Okay. We can simplify it, push the summation inside. So, there n log theta 2 minus 0.51 log 2 pi minus summation j is equal to 1 to n x j minus theta 1 whole square by 2 theta 2 square. This is my log likelihood function. I am asking which values of theta 1 and theta 2 maximize the log likelihood, right. So, how do we maximize the two is a function of two variables theta 1 theta 2, we find the partial derivatives and equate them to 0, right. So, we will do dou L by dou theta 1, dou L by dou theta 2, equate them to 0. What will be dou L by dou theta 1? If I differentiate this respect to theta 1, derivative of this is 0, derivative of this is 0, derivative of this will be half summation of this half x j minus theta 1 by 2 theta 2 square, right, into minus 1, that minus will cancel. So, if I equate that to 0, this is what I will get, j is equal to 1 to n x j minus theta 1 is equal to 0, right, that half will also go and 1 by 2 theta 2 will square will also go because it is equated to 0. Now, if I crunch this, I get n times theta 1 is equal to summation x j, which means theta 1 is 1 by n summation x j. So, that is what I get as my estimator for theta 1. Similarly, partial derivative with respect to theta 2. So, I have to differentiate this with theta 2, this give me n by theta 2, this will give me x j minus theta 1 whole square, that is a constant now, 2 will also stay here. So, 1 by theta 2 square will give me minus 2 by theta 2 cube, okay. 1 2 will go away. So, minus n by theta 2, that minus has gone, 1 by theta 2 cube into this equal to 0, right. So, if I take this term on this side multiply by theta 2, so I will get 1 by theta 2 square into something and then equate to 0 and solve, I guess theta 2 hat is 1 by n x j minus theta 1 whole square. So, by solving del L by del theta 1 is equal to 0 and del L by del theta 2, dou L by dou theta 1 is equal to 0 and dou L by dou theta 2 equal to 0, we get the maximum likelihood estimators. The estimator for theta 1 is the sample mean, estimator for theta 2 square, not theta 2 hat, the estimator for variance is the sample variance. As some of you may know, 1 by n x j minus theta 1 whole square is not an unbiased estimator of variance. If I want to get unbiased estimator, I have to get 1 by n minus 1. So, these are the ML estimator mean and variance of normal density, and ML estimator variance is not unbiased. Okay. As we already seen, consistent estimators need not have to be unbiased, and ML estimation only guarantees consistency. So, sometimes we may land up with unbiased with biased estimators, but for one dimensional normal density, these are the estimators, maximum likelihood estimators for mean and variance. We can do the same thing for a discrete random variable also. Let us say x is a Bernoulli distribution, that x takes values 0 and 1 with probability p and 1 minus p. So, I can write the mass function of x, parameter is p as p power x and 1 minus p 1 minus x, x takes only 0 and 1. So, f of 0, the mass function at value 0 will be 1 minus p, mass function value at 1 will be p. So, this is the Bernoulli density. This is the mass function random variable, takes values 0 and 1, takes value 0 with probability 1 minus p, 1 with probability p. So, the mass function is one parameter, namely p. Of course, we must ensure 0 less than p less than 1. So, if I simply maximize this over all p is not what I want, I have to maximize this over maximize the likelihood over p between 0 and 1, but as it turns out, if you just unconstrainedly maximize, you will anyway get p between 0 and 1. So, what is the likelihood function? So, j is equal to 1 to n. So, this is my thing. So, I put x j here. So, p x j 1 minus p 1 minus x j, because the product it is p times summation x j 1 minus p times summation 1 minus x j. If I write x bar as the sample mean, then summation x j is nothing but n x bar. So, this becomes p times n x bar 1 minus p times n minus n x bar. So, the log likelihood will be n x bar log p plus n into 1 minus x bar log 1 minus p. This is a very simple thing to differentiate. If you differentiate, we get this, and from there you get p once again at the sample mean. Because x just take only values 0 and 1, summation x j by n will be a number between 0 and 1. So, even though I have maximized likelihood in an unconstrained manner, I am still getting p between 0 and 1. So, that is all right. So, this is the maximum likelihood estimator for the parameter of a Bernoulli random variable. Okay. So, let us summarize today's lecture. To implement Bayes classifier, we need to estimate densities. Parametric methods assume that form of density is known and then obtain the parameters from the data. Okay. An estimate for a parameter is a function of the data. For all estimation, we assume we have IID realizations of the random variable or IID data from a density, and an estimate is a function of this data, is a statistic is a function of this data. So, estimate is a function of the IID data. An estimate is unbiased if its expectation is the true value. Okay. The mean square error of an unbiased estimator is its variance, and uniformly minimum variance unbiased estimators are very good to have if we can have them. Okay. A consistent estimator converges to the true value in probability as the sample size goes to infinity. Right. Maximum likelihood estimation is a general procedure that can find consistent estimators. Okay. MLE is the maximizer of the likelihood function. Often one maximizes the log likelihood, right, just for convenience in maximization, and for many standard densities one can obtain maximum likelihood through simple analytical means. Okay. Thank you.